who have joined online. We can see you're up to about 20 odd of you now, which is pretty pleasing. And I think Carl Ashby, Wellington Structural Group, has delegated to me to introduce myself. My name is Nick Brooke. I'm a structural engineer based up in Auckland, and here tonight to talk about the work that's it's occurred now that led to the revision of Part C5 of the assessment guidelines, which many of you will have seen the revised document. I'll apologise up front to anyone online for any gesticulating I do at the screen or laser pointing and so forth. There shouldn't be too much, but it may be frustrating at various points, I guess. And I'll also apologise if I start coughing. Again, hopefully we can avoid it. So it was setting the scene a bit. It was known basically at the release of the seismic assessment guidelines in July 2017 that further work was going to be needed on the concrete buildings chapter of that document. There was a review undertaken by some senior practitioners in early 2017, which raised various issues to do with coverage of the guidelines, accuracy in some places, and possibly most importantly, the usability and the ease with which they could be applied. And then particularly in the field of precast concrete floors, there were a whole load of live issues, and to some extent still are, arising from the various earthquakes around the country. So on the back of those concerns, really concurrent with the release of the document, two technical working groups were formed. The one I'm going to talk about tonight, covering the main body of the document and all the appendices except for the appendix, at that stage, Appendix G, or C5G as a lot of people refer to it, which covers precast concrete floors, which was a big enough topic to warrant a separate group. Some of you will have been to the seminars that have been going on that separate document. It's a big topic in its own right, so I'm just not going to touch it again this evening. There's plenty of information around about it, and I'm sure some seminars or talks like this can be organised on that if there's demand. The revised document was released with a name which I'd have to say is a bit of a mouthful, the Technical Proposal to Revise the Engineering Assessment Guidelines, late last year. It took a little while to get it out the door, but it's out there now, and hopefully most of you attending have seen a copy, and some of you are probably using it fairly regularly. The main drivers were, as I've probably touched on, to extend coverage of the guidelines to cover some of the structures that we knew could not be assessed uniformly or consistently with the existing guidelines, required you to fill in the gaps. There is some new knowledge, and I'll come to acknowledgements, but a lot of work sort of ongoing at the University of Auckland in particular that was picking up on particular aspects. And then there were a few quite obvious, in some cases, errors in the original document that were corrected. I did think maybe those of you know the new document as the yellow version of C5, that I might have been wise to change the colour scheme for the presentation tonight. You'll probably be glad to know that I tried it out, decided it was pretty painful on the eyes, and so I'm sticking with the red, even though it's not technically the correct colour. So it is known as the yellow Part C5, and is marked on most pages with that colour to try and distinguish the two for reasons that I'll come back to in a couple of slides. There's quite a few acknowledgements. There's obviously a review group who I've already mentioned. The name obviously missing here, who is probably because I wasn't sure if to list him in the review group or the whip cracker or the oiler of the political wheels, is Dave Brunsden. Then there's particular acknowledgements to some of the students at the University of Auckland working under Rick Henry and Ken Elwood at that stage, who made various contributions, particularly Tayo Opabola, who responded to every query about this, that and the other thing in very short order at all sorts of hours of the night. And then getting towards the back end of the process, there was quite a rigorous technical review set up to make sure that the second time around the document was more robust as hoped. And so the various learned societies contributed quite extensively to putting together a really useful set of comments and critiques, which led to further refinement in the back end. And it has to be said, the whole thing was made possible thanks to funding from MB. Where that goes to from now is anyone's guess, but this review, which was pretty extensive, a lot of hours put in, was made possible thanks to their funding. So that's sort of the scene setting and front end. In terms of the overview of the rest of the presentation, I'll talk briefly about the use of the revised document and then defer to probably Dave Brunsden for any further questions on that at the end. Then summarise the main changes that we've made in the revised document, and then illustrate some of the really, what I think are the key provisions. And I've sort of selected these either because to demonstrate the ways that some of the new material is quicker and easier to use, or because it's a potentially controversial change, give a bit more background on why the change was made, or because there's a couple of provisions that are not necessarily immediately obvious, despite I think being reasonably simple once you understand what's going on. And then finally, I'll finish off with just a few slides which I have to emphasise are entirely my own views, regarding the overall framework, which are sort of things that arose during the course of putting together the revised guidelines, or the revised C5, which maybe are more rhetorical questions for people to think about further, rather than answers right now. So in terms of use of the new document, it's stamped pretty clearly that it's not currently for use for assessments to determine whether a building's earthquake prone. And there's some information around in various sources explaining when it can and can't be used. It's essentially a parallel version that can be used for any assessment except where it's prompted by a letter from the council asking if the building's earthquake prone. So I understand it's pretty important down in Wellington here to know what the percent MBS is so you can keep your tenants. That's really where this driver is for the moment, with a process hopefully ongoing over the next year or two to look at shifting it across to the other purposes. But I don't know enough about that ongoing task to really comment any further on it. So it's a bit of a watch this space in that sense. There will be, I think, some confusion along the way with the two versions floating around. There probably already is. There will be some buildings where the effects could be quite large, looking at comparisons between the two different documents. And so elements where a single crack forms, the new version should generally give you quite a lot more capacity than the previous version. Conversely, as I'll talk about further later on, we've switched to a different model for column shear strength, which could, in some scenarios, give you a relatively quite significantly lower column shear strength. And so depending on where a building sat and the overall behaviour, that could be a pretty significant change. And there's going to be some ethics questions involved, which at the time I was putting together this slide seemed to be exercising my mind a bit. And, what do you do if you know that the answer that you're getting using one version of the document will have quite significant implications one way or another for a building, where the other version might give quite a different answer. Fortunately, during the course of preparation of the seminar or the presentation, an email popped up in my inbox, and I think quite a few other people's, from people in this building saying that they'd completed some guidance on how to use the new version of C5. Initially thought, great, my job's done, I'll just cut and paste all those slides and sit down. But it's really much more detailed discussion of various scenarios that might arise where you've started an assessment under one document and switched part way, or where assessments for different purposes crop up. So I've not really digested that fully yet. I'm not going to talk to it in any detail, but just to flag, if you've not seen the email, the existence of that information dated sometime in the last week or so. So what have we changed? There's quite a few areas, and while I guess headline change, you could look at it and say that I think, including the various appendices, the total length of the document's gone from a couple of 100 pages to 250 or something like that. Even that probably underestimates the extent to which things have been changed, because there's been quite a few appendices and so forth chopped out or chopped down in size, and whole sections that have been switched for new content. So really, right through the document, there are changes, probably with the exception being that there's not really anything more than formatting changes to the evidence from past earthquakes section. The more notable areas, which I'll talk through, things relating to the global capacity of the building, not so much in a technical change, but explaining what we're actually trying to achieve. New guidance on material properties and some aspects of detailing. A lot of new content for calculating the deformation capacity of members, calculating the point at which members lose their gravity capacity. And that's quite significant because it affects at least a couple of significant structural weaknesses. And then we've, as I've mentioned already, switched the column shear strength model from the one that was used to one that more accurately reflects research results. Added some changes for beam column joints. And then for some diaphragms, there's some changes that could be quite substantial as well. So running through those, and hopefully not in too much detail at this stage, but as I said, the global building capacity information, this is kind of starting at the back of the document and working forwards, which maybe is back to front, but section C 5.7 now it is, contains some front-end text which, according to the authors of the original version, somehow got lost in the editing process, which spells out that basically the whole aim of assessing a concrete building, and probably any building really, but for some reason it's in C5 now, is to either look for formation of a full side sway mechanism, and then loss of lateral strength, possibly, depending on the scenario, could be localized loss of axial capacity. So you might have a wall that's got a ton of remaining capacity, but if the columns next to it are losing their ability to hold the floor up, then that's a problem. Or it could definitely come up with precast floors, where you might have plenty of capacity in the frames, but the floors are reaching their limits. Or diaphragm failure, which potentially then stops the building behaving as a building, becomes a collection of parts, and you sort of stop having any faith in your analysis at that point, and all bets are pretty much off. So those are probably not things that, they're not clauses that you're going to be referencing and using for design calculations day in, day out, but, and it's a shame they're at the back, but they should be read by everyone, I think, just to sort of keep in mind what it is that is the driver for assessments. Certainly we still see too many around the place where the idea that it's a displacement-based framework looking for sway and so forth gets lost, and it just defaults back to a force-based demand-to-capacity ratio, which fairly obviously leads to pretty poor results. We've put in more guidance regarding the existence of various different types of reinforcing steel at different dates. Probably won't affect a lot of assessments greatly, but does pick up a few subtleties here and there about changes from minimum specified strengths to nominal strengths, and puts in a provision that I'll come back to when we're talking about diaphragms, that basically for most uses cold drawn mesh is now deemed to be generally unreliable. I think it's certainly been floating in the background of assessments that we've come across and that we've done for, I guess, about a decade or so now. It wasn't necessarily clearly written down that cold drawn mesh really has very little strain capacity to start with. Once you've had shrinkage and creep and so forth occurring, depending on the situation, may well have nothing left by the time an earthquake occurs. So there could be something there. You could go and dig it up and find the bar's not fractured, but what it can actually do is really open to question in most scenarios. And then I possibly should have put in a few more slides. It's certainly information that warrants more discussion and better examination reading by people. But we've put in quite a lot of new information regarding splices and anchorage at bars, pulled some information from FIB, the ASCE documents, and put in information that should be quite a lot less conservative, rather than just relying on pro-ratering design equations from NZS 3101. There's now equations in there that recognise the basis of code development equations, and should hopefully line up better with what you'd expect a splice to do if you tested it in the lab. There's some information that should probably be caveated, and that we'd certainly welcome feedback on over the next couple of years regarding welded and mechanical connections. In all sorts of scenarios, both for new and old buildings, these are a bit of a hot topic the last year or two, I guess. For assessment purposes, we've gone through and categorised various different types of splice at various dates as to whether they're generally going to be able to develop the bar capacity in terms of yield or ultimate capacity. And then there's some words in there explaining that if you have something that can only develop the yield, then that more or less becomes a force control, sort of brittle type local element. It might not mean the overall structure is brittle, probably won't. It might not even mean the overall element is brittle, because there's an unanswered question. If you've got a wall with 100 couplers and one of them goes bang, but the other ones still hang on for a bit longer, then what's the implication? So there is some judgment required. There's just simply not the information available at the moment to put the numbers to this in the way it should be. So as I say, if people are getting strange results using this part of the information, let us know. Feed it back through Engineering New Zealand or direct to me is fine. It might take a while to respond to, but it would be useful to know what the outcomes are from this part of the document. I didn't really list out the changes made, but as I said, a lot of the focus has been on improving the utility and hopefully the accuracy of the guidelines determining the rotation capacity of members. One of the big changes is that we've introduced what we've termed the direct rotation method. Essentially, it's an alternative to, rather than running through and undertaking a moment curvature analysis, and then back calculating where you're going to get bar buckling occurring and shear failure and so forth. Instead, there's basically some tabulated information giving you rotations directly off, which are experimentally calibrated values from which you can just look up a table and get that the rotation capacity is 1.5%, rather than having to run through, get the computer open to do the moment curvature. And we'll go into this a bit more, but I think it really is a step forwards in usability. And for those who are familiar, it's basically what ASCE 41 in the US has done for a long time. Some of the information we've used is pulled straight from their information with calibration factors to make it fit the overall aims of the assessment guidelines. Other parts are developed from alternative sources, but it really is a quicker way of getting to the rotation capacity of a member when you, and you know, it's in most cases literally a one-liner. And so spelling that out, I guess, the traditional process for moment curvature getting through to a rotation capacity might be something like get the geometry, moment curvature, convert that to a rotation by determining the plastic hinge length, then check if shear limits things, and whether that's before or after yielding. Then look into things like bar buckling and anything else that's going on. Then you get to the rotation capacity. The direct rotation, you've got the geometry off the drawings, run some quick checks to see if it's a shear governed element in the sense of 2m upon L is less than the shear, more than the shear capacity, in which case shear govern, stop the clock and head down a different track. If it's not, then it's normally, as I say, a one-liner to then get the rotation capacity out. So it can be a pretty quick process to apply. We've put in guidance on a couple of different effects that can limit performance of members based on their overall deformation. So rather than bar buckling or section behaviour here. We're saying the situation where, say, a wall just deforms out of plane because the compression gets too large. In that case, we've adapted information from Paul Ann Priestley's paper way back in the early 90s. Some of you might pick up that there's been some pretty high-end research going on in this space the last few years, particularly at the University of Canterbury. We would have liked to input some of that information, but couldn't get it into a form that made sense for design use in the time we had available. So it could be a sort of watch this space. And again, I guess if you have feedback that this is giving funny results, let us know. Columns are also covered in a sort of related sense. We've lumped them together because it's, again, an overall member effect. And for those of you who've been going to conferences and things for a while, you might remember Jeff Matthews presenting results back early in the 2000s, where at a certain point, if you don't have intermediate columns tied back into a building by a decent positive tie into the floor, then the elongation of the beams can cause the whole thing to just pop out sideways. And obviously, if you get that occurring over enough floors, then you may well end up with a stability problem, that you've got too much axial load on too long and unrestrained length, and a potential problem occurring. I'm not sure if anyone's really sort of definitively linked this to big picture problems in buildings. It's something that you could see could become an issue, and it seems like it's a relatively easy thing to cover. This is one of the topics I'll come back to later on in a bit more detail, because we refined the wording a few times around these provisions, hopefully got it into a place where it's fairly understandable, but certainly the early versions seem to provoke a bit of confusion from those in the technical review groups. So seems like something that's worth elaborating on slightly, because I don't think the calculations are very hard. It might just be that we've not explained them very well. We've provided some much better guidance on, thanks to mainly research at the University of Auckland in the last year or two, on how to handle situations where deformation concentrates at a single crack. In Christchurch, that was fairly infamously caused in a number of situations because there just wasn't enough reinforcement in a member, the gallery apartments being the one shown here. Alternately, and I think certainly in a few cases in Wellington this has proven to be the case, you can have, for whatever reason, reinforcement that terminates pretty close to the critical section, doesn't cross the critical section, and so you get a concentrated point of lower moment capacity, and all the deformation concentrates in that spot. The previous approach of, in this sort of scenario, of saying, well, calculate the normal plastic hinge length that you would use for a member that didn't form a single crack, and then divide it by 5, was really a rule of thumbs, probably even being a bit generous. It was evidently a quick response to an issue identified in Christchurch that I think probably worked reasonably well for a particular case study, but then when it was extrapolated to more general use, gave some really quite weird results, and not mentioned here, but particularly with the application of the same thing to plain round bars, just gave quite strange outcomes. And what the research has shown is that, well, it's confirmed really what has been written in some textbooks for a while, that eventually you'll get a minimum penetration of yielding strains to either side of a crack, and you can argue about what that number is, but there's some guidance around that seems to fit the data reasonably well. And so now, rather than this LP upon 5 approach, you take either the minimum of the plastic hinge length calculated normally, or this 2 times the strain penetration length, depending on couplers and so forth. So it doesn't, it fits quite well into the moment curvature approach to calculating deformation capacities. We've not included this line of thing in the direct rotation approach because there's just not enough tests to really calibrate it. And I think it is one where it needs to go back to a section level approach rather than looking at the member as a whole. We've also got what is hopefully quite substantially improved content on plain round bars. and coverage of how to assess elements that contain plain round bars, because there's a fair number of 50s and earlier structures that have beams, columns, walls with only plain round reinforcement in them. And the problem really is that the general base assumption that plane sections remain plane, which we use for concrete design day in, day out, falls apart pretty badly with plain round bars, because there's no effective bond between this concrete and the reinforcing steel. So you can't really assume that the strain here is proportional to what's going on at that section. And so instead, what research seems to support is that the idea of a rocking type response describes things fairly well. And we've got coverage now, which is really, I mean, it's shown in this plot, and there's a paper in, I think this was from last year's NZSEE conference, showing the basis of the model and how it's developed. But really, when it comes to applying it in practice, it's a single line equation, depending on the moment and the moment to shear ratio, I think it is, that then gives you a rotation capacity. And if you read this paper, it emphasizes that while this looks like a pretty steep drop-off, the gap between A and B is actually a pretty large rotation capacity, as long as the axial load is not too large. So it can be a pretty dramatic change here from the previous approach of assuming it was reinforced concrete but dividing the plastic hinge length by 5, through to a model that reflects what's going on. And so if you've got clients looking at retrofitting structures with plain round reinforcement based on earlier assessments, it may well be worth their while to revisit them with the new guidance, and then try and work out the ethics of what needs to happen from there with respect to council regulations and so forth. Loss of gravity support is now covered. Somehow this basically didn't make it into the July release, despite it being the basis of 2 of the severe structural weaknesses. So there was a bit of a gap there. This, in a lot of cases, could be pretty catastrophic, obviously, but it may not be that important for a lot of scenarios. But where it is, you obviously need methods. So we've pulled things from various different sources, and I'll come back a bit more to the approaches taken later on. But it's not a tricky thing to calculate. They're, again, pretty simple equations, but they're in there now. And if you need them, then they're there for use. Beam column joints, we've made a few corrections which have been out for a while now. They came out as an erratum, so they are, I think, actually part of the earthquake-prone building legislation now, or the approved methodology. Those are obviously carried through into the revised document overall. And we've also reintroduced the content in slightly modified form that was in the 2006 guidelines that explained that if you have a poorly reinforced beam column joint and put a large deformation next to it, so a large plastic rotation in the beams adjacent or the columns adjacent, then the joint tends to degrade. And so this has come back in again. For some reason it got lost in the July version. And so depending on the scenario, you might well get quite significant deformation, quite significant degradation of capacity if you're trying to push old joints out to large curvature ductilities next to the joint. And I won't dwell on it here, but we've also introduced some content covering modern beam column joints, for want of a better phrase, which previously I think people would have just said, well, it's not that important to have coverage, we can just use 3101, but the feeling was that that's a fairly conservative approach for a lot of joints, and there's some better information out there. Unfortunately, we've had to put in 2 or 3 different approaches, depending on whether it's an interior joint or an exterior joint, and the precise scenario, because there's not really sort of a coherent model that pulls them all together at this stage. So for any of the academics in the room, there's an open research topic there to look into what works best and try and develop a consistent model that works across all cases. So there's a bit of content to work through, but hopefully it might be of use for some assessments. And diaphragms have had some changes. Probably the most significant in terms of direct impact is the explicit statement made that you basically can't include cold drawn mesh reinforcement in a strut and tie model. We've scratched our heads and tried to work out if there's a way that you can sort of hold your hand behind your back and hope and ascribe a capacity to it, but basically there's no way that you can work that through, and I'll come back to that. That obviously creates problems for quite a number of diaphragms, particularly from the 80s, and so there's to try and mitigate that impact, because the feeling was that obviously a lot of these diaphragms have a capacity, it's just how do you work out what it is. There's now 3 different approaches covered, and I'll come back to what they are, but the one that's probably of most interest is the deemed to comply sort of approach, that for certain diaphragms you can actually get away with saying, well, in a moderate earthquake, this is just not going to create a life safety risk, providing the precast floors stay intact, without actually doing any checks on the diaphragm. So that brings us to talking through a few of the key provisions. The direct rotation method, I'll sort of illustrate how that gets used. Some discussion of why we've switched the shear strength model, which it could well have a fairly negative impact on the strength of some columns. So we had quite extensive debates internally, and then trying to convince people that this was a necessary change. So there is a pretty good reason for it. Then a bit more discussion of axial failure of columns and some changes made to the severe structural weakness, which I sort of skipped over in the fact that there has been changes there in the summary of changes. Then an illustration of how to apply the lateral instability of columns, and some discussion of the diaphragm changes. So we had this slide earlier on, and so to illustrate the change or the difference between the moment curvature process in blue at the top and the new direct rotation approach, basically we're going to pull a fairly typical but not that great column and just work through the 2 processes in a pretty high level sense. I'm not going to run through every calculation here, but just sort of illustrate the steps involved, which hopefully shows that the new direct rotation approach is rather quicker to apply, and I think less prone to user error and more able to be directly calibrated to what's observed if you test columns in a lab. So we've undertaken step 1, get the geometry. I could have talked through it on here, I guess 600 by 400 column. You might notice a discrepancy here. I've just said it's 6 25mm bars. The actual column had a couple of 16s instead, but it doesn't really make a difference here. And some stirrups at spacings that are 200mm, so a bit too far given the dimensions involved. And so I think if you check those against the provisions, they say that basically there's no effective confinement going on in this column. So that makes the moment curvature a bit easier, I guess. So we can run that through, and this is response. I'm sure plenty of you recognize it. You get a moment curvature curve out, and you can pull that out and put it into Excel. But to then take that forwards, we obviously need to convert that to from a curvature to a rotation, and so we have to run through and calculate a plastic hinge length, and we'll also convert it from a moment to an equivalent shear based on the column length or assumed column length, which then makes it easier to compare to the shear capacity equations. And so there's a couple of different steps to the integrations of curvatures, and you need to do the elastic curvatures on one basis and then add on the plastic curvatures on a different basis. But you can run through, it's not too big a spreadsheet, but there's some steps involved. Then we run on to the step of determining the shear capacity, and in this case find that even on the new shear model, there's enough shear capacity to yield the column. And because the column itself drops off, and I think I assumed here a 5% axial load, ratio, the backbone of the moment curvature remains below, or the flexural response remains below the shear response. And so, at least on these calculations, the thing behaves in a flexural manner. But one of the big concerns with this sort of moment curvature shear interaction approach has been for quite a number of years that you've got scatter on the shear strength, maybe some scatter, but not as much on the moment curvature response. And this itself could be open to interpretation depending on the confinement of the column, the spooling strain, and so forth. And I think, in fact, if I'd paid a bit more attention, this moment may well have probably more realistically increased a little bit further. So maybe it was going to intercept with some better assumptions in the moment curvature. But if the shear strength came down a bit, and you're assuming 45 MPa here, what if it is only 35 and it drops down to this point? Then suddenly you've got a shear failure occurring at a point that has a pretty shallow angle of intercept between the two curves. So there's quite a lot of room for interpretation there of what's going on, which directly affects the outcome of how far you can say that column will be pushed. And then we jump to the next step. We need to run through a check to see if the column's limited by bar buckling. Unsurprisingly, we've got 25mm bars and stirrups at 200 centres, so there is a limitation here. This is an equation now in the guidelines. It replaced one that was there previously. It looks pretty similar, but has an imported bottom end limit so that you can't get a negative strain out of it. And so that drops in, and it actually turns out to be pretty close to the point where the concrete starts crushing in this example anyway. So we end up with a rotation ductility of something like 4 dropping out of this approach. And you can run through some more maths and spreadsheeting and things. And if I've done it right, translate that to something like a 0.01 plastic rotation for the column. So most of this is probably pretty familiar to a lot of you, teaching you to suck eggs, maybe even. It's really done, as I said, to contrast what we'd do for the direct rotation method. There's different approaches depending on the type of element you're looking at. So for beams, there's a bunch of values just tabulated taken from ASCE. For columns, we've modified some of the equations that are given in ASCE. There's obviously a few more parameters that need considering, which make tabulation a bit less practical because we've got things like shear and transverse reinforcement ratios creeping in. And then for walls in particular and a few other elements as an option, we've got an approach in that's basically taken the KD type approach that 3101 has. So you could argue that this is still in some way related back to curvatures and so forth. But the key difference between this and the general moment curvature approach is that all these KD limits are experimentally derived rather than a moment curvature analysis, which relies a bit more on getting the computer model to be running correctly. All of them are pretty quick and easy. There might be more than one line, but they're not more than half a page of calcs in any particular instance. So in the case here, we take the column equation and we plug in the axial load ratio, which I said was 0.05. And then I haven't gone into detail, but you can calculate the shear demand and the shear capacity and plug those in, and pretty quickly drop out that the plastic rotation is something like 0.015 radians. You shouldn't draw too many conclusions from the fact here that this is given a number that's 50% bigger than the moment curvature response. It could be bigger. It could, I think, in some scenarios, give a smaller number. The 2 points that are worth taking away probably are that the evidence I've seen is that generally the direct rotation method, at least for columns, which is where it's been examined quite closely, will tend to give a less conservative result than moment curvature, because what happens is with moment curvature, you happen to make a slightly conservative assumption on the spalling strain, and then a slightly conservative assumption on something else, and then a slightly conservative assumption on something else. They all just compound a little bit at a time until you've tuned into the capacity, whereas these values, leading to the second point, The equations are basically empirically derived by plotting out a whole bunch of column experiments and saying, well, this one had these parameters and got to here, and then fitting a regression line through and saying, so on average or on 10% chance of exceedance, the capacity is X. And so they, as I say, will, I think, often be a little bit larger. And generally, I think I'd have more confidence of plucking one of these numbers and knowing that it has a reasonably good chance of relating directly to the actual behavior of an average column. I better speed things up a little bit. Column shear strength. Historically, and it remains the case for walls, the guidelines have used the so-called UCSD shear model, developed out of a bunch of bridge column tests conducted in San Diego in the 90s, including by Jason and a few others. That genesis gives also, I think, what has proven to be the weakness of the model, which is that most of the calibration data used to derive the model was from circular columns with fairly squat aspect ratios. So the bridge columns, Jason could tell us better than I could, but probably 1,200 diameter and a couple of meters tall in the lab specimens. Whereas when you look at a broader database, and this paper or the new model is Sazin and Maley's model, looks at a broader database, and then someone called Vecchio, an Italian guy, has just recently and quite conveniently looked at a very large database of columns and parameterized it across a whole range of different variables, geometry, aspect ratio, different types of failure, and so forth. And while it might be a little hard to see on screen here, these top values for the UCSD model, essentially this ratio here is the ratio of experimental shear to the predicted shear. So ideally you want that to be a little bit larger than 1, so you're getting a higher strength than you're predicting, and then you can adjust from there to give the margin you want. And the UCSD model does a pretty good job for certain variables of predicting what the strength is, but then for others, and probably most concerningly, and I'll go to the next, sorry, I'll stay where we were, for rectangular columns, tends to predict a strength that's on average only about 90% of what you get in the lab. Sorry, other way around. The lab strength is about 90% of what's predicted, which is obviously not a very good place to be. And without going into the exact values, the same is found when you have more slender columns. And while the data is not given there, I don't think it's reasonably easy to imagine that these two might compound. And so if you had a slender rectangular column, you could actually end up with a reasonably significant overprediction of the shear strength. This replacement model, on the other hand, proves to be much more uniformly predictive of a strength that's just a little bit higher or a little bit under what you get in the lab on average. And so that's a pretty good place to be. This table basically takes the same data and reproduces it in a different and probably easier to read form. But the key headline number here, I guess, really is that where we were in the July 2017 and before that, the 2006 guidelines was a UCSD model with a 0.85 factor applied. So on average, you got a strength in the lab that was 1.06 times what you'd predict using that model. What we've gone to now is just a direct adoption of the model postulated by Sazin and Maley, no 0.85 factor or anything. And that gives you, on average, 1.09 times higher strength than you predicted. So across the board, there's not a whole lot of difference. But where you will find more significant differences is that the Sazin model, again, shows up here as being pretty uniform, whether you're looking at rectangular or circular, slender or squat, whereas the UCSD model had quite a bit more variation. So if you look at rectangular columns, you will find that there's some significant drops compared to what you would have predicted the shear strength to be. But we think it's definitely the more correct way to be doing things. Deformation at the loss of gravity support. I won't pretend that this is the be-all and end-all of every assessment. The relevance of it really depends on the configuration of a building and what you've got in it. if you've got slab column connections, then it will probably be the key performance check, because we're recommending in the guidelines that you ignore any lateral resistance from the slab column connection, because normally they'll be a whole lot more flexible at low levels of load than the frames that you've hopefully, or the walls that you've hopefully got in parallel with that system. And so really the performance check on whether the slab column connection is okay or not is going to be, does it hold the floor up? On the other hand, while I'm going to talk about columns here tonight, just briefly, it will probably only ever come into play where you've got a secondary column sitting in parallel with quite a stiff and well-detailed wall, because otherwise you're going to, if we go back to a slide we had earlier and I didn't really dwell on, we've got these goals of maintaining lateral strength at the percent MBS value. Across the board, you'll find that the lateral strength is lost before you lose axial capacity or at the same value. So if you've only got columns and frames in a building, then you're always going to be limited by this performance point rather than by loss of gravity. It's only if you've got something else that can hold up the structure once the column's gone past this point that it will be of interest. And so I guess the classic example in recent years would be, say, the CTV building. If it had been held together better, you could end up with a situation where, sure, the columns aren't contributing anything to lateral strength. Maybe they weren't in the first place, really, but if they'd had enough capacity to hold up the floors, the walls could keep doing the job there. For columns, the model adopted is from ASCE, which basically means it's Ken Elwood's model, and so I've stolen one of his slides from a decade or so ago to show the basis of it. I guess this is up here to emphasize that it does have some mechanical basis. It's not just a total black box. It's quite a sort of simple, elegant kind of model, which translates through to the guidelines as another one-liner equation. And basically, depending on the axial load ratio, it gives you either very large drift at the point that you lose gravity capacity or a rather small number. And it has to be borne in mind that if you're now beyond an axial load ratio of 0.2, this number could be decreased further because we've changed the non-ductile column severe structural weakness. So where previously it kicked in at an axial load ratio of 0.5, it's been dropped down to 0.2. The reason being that the previous limit didn't actually capture the columns that it was meant to, or that it was instigated by in the first place. And there have been a few other changes and tweaks to the definitions of lightly reinforced and so forth. So worth a read of that section just to get a feel of what's going on there and be on the lookout for those. Column lateral restraint. This will generally only be an issue for buildings pre-1995. Changes to the concrete standard kicked in at that point, so hopefully everything after that has reasonable ties to keep things held together. I wouldn't stake my life on that being the case in every situation, but as a rule of thumb, that'd be, you're looking at 80s buildings with this. And basically, going back, and it has to be emphasised based on a single test result, more or less, with hopefully a few more to come over the next year or two. The judgment has been made that columns that aren't tied in well to a floor plate will detach from that floor plate when the drift at that level exceeds 1.5%. And once that happens, there's then two performance checks. You've got to check whether Euler buckling load is exceeded or whether the slenderness ratio is exceeded or breached. And some of you will note this is very much the design equation from 3101. So you probably can, if you can convince yourself with some more detailed checks that this one's not so relevant, work around it. But if we run through the same 400 by 600 column again, you can reasonably quickly draw up curves, assuming a story height, that give you either the slenderness ratio or the Euler buckling load, depending on how many detached stories occur. So that's sort of the background information that you then use running the performance checks. And if we say that that's in a 12-story building, just drawn up quite arbitrarily, and then say a yield the drift might be about 1%. So there's no disconnection at that point. Then if we say, well, what happens at ductility at 1.5, peak drift might be about 1.4% then, and so there's no disconnection at that stage. Then if we push it a little bit further, the drifts exceed 1.5% over something like 5 stories. And so suddenly, if you look at the 5-story line here, we've well and truly exceeded the slenderness ratio of 100. And so we'd have to be saying, well, that column is at risk of buckling. Maybe we can look into that geometric sort of relationship a bit more and say, well, we can get around that. But you're down to a load limit of about 0.15 AGFC. That's still not too bad. Push it a bit further and another couple of stories disconnect. And so then at that point, you've really got quite a low residual load carrying capacity in that column. Probably won't come up for a huge number of buildings. As I say, focused on the 80s sort of building stock, but a hopefully reasonably applicable check, not too difficult to do if you do need to. So I think the last of these sort of provisions in a bit more detail, some of the changes on diaphragms. Hopefully pretty much everyone here knows that the current sort of position in New Zealand is that for general purposes, diaphragms have to be assessed, analysed by strut and tie methods. And that's all good, but we have to remember that strut and tie is a plastic method of analysis, and there's no checks on deformation compatibility when you're doing it. So you postulate a mechanism and say, well, I'm going to have some forces running to here and here and have some reinforcement running across this point. You never check what the strain and the reinforcement is, and the method basically doesn't give you a way to do that. And so to actually mobilize these mechanisms, you could end up with some pretty wide cracks in locations that you really don't know what they are, and certainly don't check what the crack widths are during the process of assessment. And what that means is that the method is basically incompatible with mesh that has such low strain capacity that it could feasibly be fractured by shrinkage strains prior to the earthquake, or movement of vehicles through a car park, or any number of other causes. And so basically we've said, if you're doing strut and tie, you can't rely on this reinforcement. And that's why this sort of thing's observed fairly regularly, bar up the top there in case it's not come through quite so clearly. That obviously creates a bit of a problem for some diaphragms, as I've already said. And so there's kind of 2 outs that might work for you in that scenario. The first is to undertake a purely elastic analysis where a bunch of things have to be satisfied. I'm not totally clear how that's undertaken. It was something sketched up at fairly short notice around a table to try and sort of capture what we thought might be going on. Probably needs a bit more thought and work to determine whether it's the right way to go or not. What does have a bit more, it's still very much a bit of a judgment-based thing, but there's a qualitative approach that's been introduced which can be applied to certain diaphragms. And as I said earlier, if your diaphragm hits all of these targets, then you can make the assumption that it's not a life safety issue during the prescribed moderate earthquake. So you can't say that you're building 67% MBS without doing some more detailed checks, but you don't need to worry about whether you can actually trace a diaphragm load path in detail to prove that it's not below the earthquake prone threshold. There's obviously a bit of a sort of what's going on here, catch-22, that we're not allowed to use this for the earthquake prone building checks. So it's kind of with an eye to the future, I guess, but it is what it is at this stage. And I won't run through these, but basically the bottom 2 could be rephrased by, if you can draw an overall sort of load path of struts and ties from the main points of the frame through the floor plate, then you're probably not going to have a problem. Whereas, say, this scenario F, you've got a discontinuity at the end of this beam where you go, well, there has to be a tie force in that beam. Where's that going to go? No, there's nothing in the floor there. And so that's why that KSF would need to be checked explicitly, whereas if there was a beam running across here, you'd be okay in that scenario. So it might be a little hard to interpret some of these words. If it is proving a problem, just try and remember to think of it in that context of, can you draw a big picture strut and tie for the diaphragm? If you can, then it probably falls into this category. And finally, I've just got a few slides which, again, I'd emphasize are really not content of C5, but just sort of thoughts provoked during the development of the guidelines and having to think about various things. And I'd have to say, and hopefully acknowledged appropriately by some of the comments received from the technical review groups. Just a few thoughts for people to take away about the overall framework of the assessment guidelines as they are at the moment. And the main one, I guess, is the issue of reserve capacity. And so there's sort of an ongoing debate that I've had with various people, mostly around our own office, I'd have to say, as to, if you do an assessment, and this has gone on for about 10 years, if you do an assessment and a building's 50% MBS, does that mean that at 51% MBS shaking it falls in a heap, or does it mean that actually it keeps going? And I think the guidelines in the front end are pretty clear that the intention is that there's a decent margin there. So you're not expecting brittle failure just beyond the percent MBS rating of a building. And there's various different clauses that talk that through in this multicolored diagram. Multicolored diaphragm would be interesting. That put this across, that basically, if you've got a 50% MBS building, there should be a margin before things really go bad and things start falling apart. And there's talk about that should be similar to a new building. And if you look in 1170.5, sure enough, there's some discussion in there about margins for new buildings and statements that there should be an assumed margin of at least sort of 1.5 in a building, and that there should be a pretty low risk of falling below that. And I don't know the steel standard well, but this certainly carries through into the writing of 3101, for instance, that if all the would be a really chance of falling below that stated margin. That, unfortunately, as far as I can work out, doesn't flow through into the guidelines as they're set up at the moment. The guideline framework can quite easily provide a margin on members, and that's what prompted these review comments to come into the group, that the review group had focused on making sure that there's, if the assumed rotation capacity of a column is 0.04, the guidelines will say it's 0.03 and there's a 33% margin, or whatever the calibrated value is intended to be. And so there's a best intention there. But what that actually means when you put it into a building, and where you've not got the benefits that you have in design of capacity design and predictable sway mechanisms and the like, is that the margin really becomes quite dependent on how the building overall is going to perform. And so if it's a low ductility, soft story situation, the same margin on the same column will give a much lower overall margin beyond where you think you are than if you have yielding occurring over the height of the building. So that's sort of something that's missed in the guidelines as they sit at the moment. I don't know what the answer is there, but there's more discussion needed to be had. And to me, it really leads to the elephant in the room, which to me is an overall question of, is it actually useful to try and rate a building relative to a new building? We don't try and do that for cars. We have minimum standards for old cars, and you have to make sure that the seatbelts work. But no one's saying that my junky old Mazda has to be brought up to a certain proportion of a new Bentley. It's just sort of a user beware kind of thing, that a new car might be better. But we've got caught, I think, into this idea that it's a useful thing to do for buildings. I've talked about the fact that I don't think that comparability is there for the margin in a detailed assessment. I think there's also issues that arise of whether IEP type assessments have as much relation to what's really there as we would like them to, and I find it pretty hard to see how the values can be expected to compare in any particular way to a detailed assessment of the same building, because the assumptions are so idealised in the basic derivation. And I don't think there's really a way around this. It's got to be something that's accepted, but I'd be pretty uncomfortable about rating a building solely off an initial evaluation. And I think the one that really gets me most about the whole thing is that percent MBS, to me, has questionable utility for engineers, but where it's a real problem to me is that it's wide open to interpretation by the public, because it sort of implies something that they think they can understand, then run away with it and ascribe it all sorts of meaning that it doesn't really have. And so we've had discussions with people we thought were pretty informed about these sorts of things, and then left the room wondering how on earth they still think that 67% depends on whether, or relates to whether they should insure a building or not, and thinking that if they can upgrade a floor to 67% MBS, then their insurer might be less on the hook for damage, where obviously the two things are not really related at all. So I think we've given the public a term that they can grab and think that it means something where maybe it actually doesn't. So that brings me to the conclusions. I won't reread all of these. I'll just pop them up on screen and leave it at that, I guess. Understand it's all pretty late, so I'll open it up and happy to take any questions. I'm not totally sure. I'm sure someone here can wave if we have a way to take questions from outside the room, but if anyone here has any questions, feel free to fire away. Stunned to silence. It's all right, I'm ready for dinner too. So I'll pass the headpiece. I've got no real problem with doing so. I'm not sure what the structural group's normal plan of doing that is, but yep, we can make that work. I'll leave it to Carl to communicate the information out. And on that, I'll pass the mic over to Carl to close things off.
I'll just hang on to the thing here. Yeah, look, thank you very much, Nick. That's been rather brilliant and very short. Believe me, it's short for the amount of changes to the guidelines, but very, very topical and getting to the right point of the nub of the issues presentation. So I'd like to thank you on behalf of the Wellington Structural Group, and we could all put our hands together. I actually don't have anything more to actually say for the rest of the night, other than that's it. And thanks to all those online. I'm happy for you to email me, carl.ashby@wsp.com, and I'll get these notes to you out in PDF format in the next week or so for those online. Okay, thanks.